Okay. Welcome. Just you and I here, Richard, on Samba. And we're going to be broadcasting this on YouTube, the YouTube Live, for those who want to participate there. And that means it'll also be recorded for later. But we're going to extract a piece of video from a training class, Richard, that you did for Grease Thief Boot Camp. Which was really something that was done over a series of days, part of our Grease Thief Boot Camp to prepare laboratories who have the Grease Thief Analyzer and other associated instruments for D7918, and those who wanted to learn more about it and see if this is something that they could bring to their laboratory and expand their ability to offer to others. And so we took that recorded session from something that was done probably in the middle of the night because we timed that for the folks in Asia. But it was really nicely done by you, Richard, and I thought that's something we could share with folks today. So I'm going to bring that up, and we have it on screen here. I'm going to start that, and then I'm going to duck out, gives folks a chance to follow through with this, and then we'll see if there's any questions that come along in YouTube Live or here in Digital Samba over the course of it, and it'll be about an hour, and we'll come back to discuss those questions at that time. So we'll get things kicked off. Anything to add, Richard?
Nope, that's what I was going to be. My one comment was if anybody has any questions, feel free to throw that in the chat during the video, and then we'll make sure we'll cover all the questions at the end.
Yeah, that chat will work here in Digital Samba. It also will work in the YouTube live chat as well. And so here we go. Richard Janoski taking us through the process of analyzing greases for consistency using die extrusion and also doing particle counting of the extruded grease film.
Die extrusion and grease particle counting, and both of those are done via ASTM D7918. So that's our standard for in-service grease analysis. So we'll start off with talking about our Grease Thief Analyzer you can see here. So here I have a Grease Thief sample. This is how our sample inside a shipping tube arrives to the laboratory. And then we've already performed our ferrous measurement on this, and it'll get to our analyzer. The first thing we're going to do is going to prepare this sample for our die extrusion. And there's a little bit involved in that, and that'll help prepare the sample. So that way we're running the sample the same way every single time. And the way we're going to do that is we're going to grab an extrusion die from our bag. And here you can see that die, and it's got threads on the inside, which are going to be able to allow it to connect to the Grease Thief. So I'm just taking that cap right off the end. And then I'm going to take that Grease Thief, and I'm going to thread it into my extrusion die. And now it's going to be prepared for extrusion. And then the next thing we're going to do is we're going to put this inside of our analyzer, and we're going to put it on the heating rack. So I already have a couple samples in here as well, but then we'll be able to place this up on the heating rack, and we can see that those samples are up there, and that's going to allow the samples to come to a consistent temperature. And then each time we're running the test, similar to a viscosity test where we want to run at the same temperature each time, we would be running our grease test at the same temperature each time that we perform it. So I've loaded that in there. The next step in our analysis process while our samples are heating up would be to perform the calibration. So I will take my calibration. It's got a spring inside of here, and I will load that up as if it was a sample. So once I get that loaded in place, I will then show you that. So we've got our calibration standard loaded up in the holding holder there, just like as if it was a Grease Thief. So then I'm going to go ahead and close the door, and then I'm going to run that calibration. And so during this calibration run, it is going to ensure that our load cell and everything like that is still within the calibration that the unit came with. And in the software, there's a simple check that you would download the run when it gets done and completed. And then it has a pass or fail. It lights up red if you would need to adjust or make a standardization to the unit. And then you will able to complete that. And then it looks like it is done. Yep, it's done. So then we would just return that to the home position. That's going to lift everything back to the starting position. And then we'll be able to pull that out. And then we are now ready to go to be able to run our samples.
So Richard, on that, you have a spring inside that has a known K constant value, so that as you compress the spring more, you expect a load profile to develop from that. Is that right?
That is correct. And then that is what it is checked against. And it has to be within that that constant of the spring to pass the calibration. Yep, you are
Great.
correct. So now that our sample is prepared, I had some other ones in there heating up, so we'll be able to run. We won't have to wait the full, we suggest waiting 10 to 15 minutes just to make sure that the sample has time to come to equilibrium to that test temperature, and then we don't have any changes in the way that the samples run. So the next thing that we need to get ready is our substrate. So this is what the sample is actually going to get extruded out on. So this is just two thin layers of plastic. One's the base that supports it, and then the top is a thin layer that you can kind of see those individual lines on there that are pre-cut. And then once the sample is extruded, we'll be able to pull off those individual sections. And then each section, kind of as you've seen before in the training during boot camp in the pictures, is that, 2 would be for RDE, 1 would be used for color, 1 would be used for FTIR, 1 would be used for moisture. So we'll go ahead and load that up, and I'll get this in here, and then I'll show you what that looks like loaded up. So we simply are going to put it in the table. The table has a groove that holds it, and then we have a little lock that holds it in place. All right, so you can see at the end of the table there, the little switch is flipped to the right, and that's holding our substrate in place. And then you can see, I'll lower the camera, the substrate is flat or even with the table because of the
Richard, could you point at the
Yes.
little lever that you were
Yep.
talking about there?
Yep, and I can undo it. So there I have it loosened, and then there I will tighten that.
Okay, very good. Thanks.
Yes, no problem. All right, so our substrate's loaded, and then the next thing we're going to do, could have left that door open, is going to be loading our sample up. So the one thing that's going to be important to remember is that there is this will be easier to see because it's coming out of this one. A small or thin film. It'll be like a thin ribbon of grease that's going to get extruded out of the extrusion die. And you can kind of see it coming out of the edge there. So it's important that that is going to be facing to the right, because that's the direction that the table will travel during the test. So I'm going to load this up in here. So it'll be just the same way as the calibration. I will make sure that I'm pushing the grease thief back into the holder, and then I'll turn the wheel and lock that in place. And then I'll get closer so that you guys can just see that. So you can see there that you've got the grease thief, and you've got the silver little arms on the side. So I can kind of, right here on the left and on the right, you've got those little arms that are holding on the smooth part of the grease thief, and that holds it in place to make sure that each sample is run the same exact way. So now that I have loaded my sample up, I am going to wait. And right now, right here on this screen, I can see that the temperature is just a little bit higher than our test temperature. We do our testing at 30 degrees plus or minus 1. That's 30 degrees Celsius. So we're going to wait for that sample to come down. And the way that I know the temperature is that there is a thermocouple here to the side of the greasy, so you can see those two little orange rubber bands, not rubber bands, but sorry, but like orange pieces on the side of it. And that's pointed right at the grease thief. And that is taking the temperature, and we calibrate that using other thermocouples to make sure that we're getting a good reading. So we're getting close to the test temperature. So I'm actually going to set the camera up inside of the unit. So that way when we run the test, that you guys will be as close as possible to viewing this. Does that look okay, Rich?
Richard, that looks like a good angle there. I think we'll see the extrusion.
Okay. Thank you. Okay. So we just hit our test temperature. So I'm going to go ahead and on the screen on the outside, I'll hit start. And then our test will start to run. So at first, it'll be what's just doing the fill at the beginning of the load profile. This is just making sure that grease is coming out of the extrusion die as well. And then it's going to go through 3 different speeds to test load profiles or how it reacts. So you kind of right there, we see it looks like it slows down for a moment. It almost doesn't look like it's moving just because of that speed change. And then after a set time, it's going to increase in speed. And that's going to be able to see, and we've seen this in the graphs in boot camp that Rich shared when he was talking about this, but it's the force profile of the grease during the set profile. So if a grease has gotten harder while it's in service, it's going to require more force to extrude it over that set profile. And then inversely, if the grease has gotten softer, it'll take less force to extrude it over that profile.
About each section holding 0.25 grams of grease approximately, but I can see on this particular extrusion, there's obviously some variation. So can you talk a little bit about why you see that and how you handle samples like this?
Yes, I'd be happy to. So sometimes it can be challenging for the customer to take a sample without getting like an air bubble in it or something like that, depending on how they have to take the sample. So this one could be that from our customer, where this could have this could have had 2 small little air bubbles, and I'll pull this out and get this closer to the camera so you can see what I'm talking about. And then I will return the table so that we can run another sample in a couple minutes. So as Rich pointed out, right here we've got 2 sections where my fingers are kind of touching, where the grease stops, and that is an air bubble in the sample. So that kind of causes a break. And what we'll see in the extrusion profile is we'll see a dip in force. And with the software, we're able to select or deselect that data and make sure that it doesn't count against the load profile of the grease. And then we don't have an influence of air making the grease, look like it's softer over the average of the force reading. And then, as Rich mentioned, if it's a full grease strip, so down here on the end, I have a nice run. There wasn't any air bubbles. These strips would have a nominal 0.25 grams of grease. So that's really beneficial then for the laboratory, where if the customer has a good sample, then the laboratory is able to take these strips right off, and we're pulling, the 2 strips off for RDE, and then we are able to put them right in the vial and dissolve them because we know that the weight is controlled on there because of the extrusion profile. And then we're not having to constantly go to a scale and weigh out the grease and kind of be going to the scale for every single test. Now, obviously, sometimes you get to the end, or if you're doing a test, like moisture, we might have to move it into the boat for Carl Fisher or something like that. Then you might have to use the hand. But then the nice thing of this is that the strip, instead of having to transfer the grease by hand, this strip can be put right into it. So when we use the Vapor Pro or when we run a Carl Fisher, instead of having to smear our sample onto the vial, we're able to take this strip and we're putting the strip right in the vial for Carl Fisher. Whether you have a boat or vial, you can put it right in there and then seal it and run Carl Fisher. Or with Carl Fisher, we're able to put that in the vial, put the top on with the septum, and then run that same way. And then it's the same way too for, as Rich mentioned, our antioxidant testing. So instead of having to smear the grease on and try and get a nice thin film around the outside of the vial, the grease sieve substrate can be curled up, slid right in the ruler vial. You add your solution, wait your time to allow the additives to be pulled out, and then run that analysis. So it's kind of, the real big advantage is that our sample is not only did we get the force value, the GTI number, the grease thief index from our sample, but then we've also prepared it. So it's not a destructive test. It's a high value test that's also prepared the rest of our analysis. All right, so I got a couple more samples. I'll go ahead and just get ready, and I'll just run another sample just to kind of show a couple being run. And then pull those graphs up. So again, actually, I'll put the camera in here so you guys can see this, and then it'll just be in here for the die extrusion again as well. So simply just taking the substrate, and it's going to just slide right in that spot in the table it's made for it, and it'll just slide in, and then I'm going to lock it in place. And then from the heating rack, I'm going to grab my next sample, and then I will bring that down, and I'm simply just going to use my one hand, push it back against it so it's flat, and then I'll turn my knob to lock it in place. And then
talk a little bit about the orientation of the die. Yeah, there you go. And also what the purpose is of pressing that in place when you tighten the knob.
Yes, so I'll move it out of the way for a second. At the back, you can see there's a flat block. So that flat block allows, when you press, that actually the extrusion die is sitting flush against that block. So that way you know that you're locking each sample, and each sample is run in the same position, and there's not kind of any angle or any kind of weird obstruction that could affect the results that we're collecting. So we've got the sample.
And then you reoriented the extrusion die right from when you first put it in. You reoriented that. You spun it around. What's the significance there?
Yes, I did. So as we mentioned before, it's going to come out when we saw the grease extruding out in the thin film, if the extrusion orifice is not facing to the right, the grease would get smeared underneath of the extrusion die, and then you would not have that nice thin film. You would get kind of a smearing of the grease underneath of the extrusion die, versus when the table is when the opening's to the right, the table carries the grease away as it comes out of the extrusion die. So you'll notice when I start this video here in start this test here in a minute, the tray is going to travel towards and look like it's going to go on under the camera, and it'll carry the grease away from that extrusion die. So we just hit our test temperature. So I'm going to go ahead and start that test. So you can see that vertical actuator is pushing down, and that's causing the grease to be forced through the extrusion die and out that orifice that extrudes it in a thin film. So there you can see that ribbon of grease coming out. And then this is again one of the slower speeds, and here momentarily we will then see the speed pick up, and it'll look like it's going very quickly. And this allows us to kind of see step changes in the grease's performance. So is the grease reacting similar to the baseline or the reference lube that's being put into the machine, or is it starting to change? So sometimes we'll see greases that have very similar extrusion profiles throughout the 3 different loads, and then others that have bigger changes. So it's kind of allows us to kind of see that grease's performance over time and see, is it changing its characteristics compared to that reference lube.
People ask about the NLGI grade or the cone penetration test. And, when I look at this, I think, yeah, that's a test that's performed on greases, but it doesn't really help us understand the dynamic or flow related behavior of the grease. And that's what this test really does. You have those variations in speed that you're pointing out. So we get to take a measurement where the shear rate is changing. It's speeding up and it's slowing down as it goes through that same flow channel that's been established in that extrusion die, which is the same every time. So we get to see what happens to the grease as it undergoes those differences in the shear, and now you've got it restoring it back to its original position there.
Yep. And that's the nice thing, is that it automatically resets to the same home position on the actuators. So it's nice that once that comes set, you don't have to kind of change, or there's not a button that you have to hold or anything. You just hit a button and it returns back.
Right.
All right. I've got one more sample to run if you'd like, or I can switch and I can.
No, let's run this. Let's run another sample. You ran one first that was a little darker grease, and it did have some air pockets in it. That second one, it was kind of a smoother extrusion, wasn't it? Was that a new grease, the one you just ran?
It was, and I can, when we pull the camera out, I can pull that one up, and I can kind of show the shark toothing that we sometimes see on reference baseline or reference greases, and we can discuss that.
Okay.
This one's got some wear in it, and we're not actually going to be able to extrude. It was an R&D sample I thought we might be able to extrude, but it's too thick. So we'll have to use this one.
Yeah, and there is some limitations here, right? We sometimes find that either greases that have significantly hardened or greases that have a lot of contaminant particles or wear particles in them will actually be unable to undergo a full extrusion, right?
Yes, that's correct. Especially grease samples that have larger particles. The larger particles can, especially depending on where they're at in the grease thief, because as we know, wear and contamination is not 100% homogeneously spread throughout our grease body. So if it's right at the beginning, the die extrusion would be clogged pretty quickly, and you might not get a full run. Whereas if the particles are at the end, you might get a full profile extrusion and then the particle effect at the end. But yeah, large particles can cause that buildup of pressure, and then it causes it to stop the machine to protect the load cell.
Yeah, of course, in the design, we created a weir feature that it tends to want to push some of the large particles off to the side to keep them from clogging. And so a certain amount of that's accounted for in the design of the flow channel. But there's a certain point at which you overwhelm that, right? And that's when we see the clog function.
That is correct.
But yet that's a data point in itself, isn't it? The fact that it clogs says, hey, this grease has changed significantly from its new condition. And that's certainly going to affect its behavior in that machine, the way it's able to lubricate effectively, move around within that environment, even its ability to be displaced when new grease is being pumped in.
Yes. So we're almost at temperature on this last sample. All right, just hit our test temperature, so I'll go ahead and get this last sample started. So again, we're going to see that speed at the beginning where it's making sure that there's grease coming out and through the extrusion die before we start getting to our test profiles. And then there we just saw it slow down, and we are in our first load profile of testing. And then just a couple seconds, we will see that speed up. And then now we're in the second load profile. And then this will go, and you'll see it slow down in between to a medium speed compared to the other two for the third low profile. All right. So then go ahead and remove my sample. Actually, I'll leave this in here one last time just to show the table returning again. Close my door. And then we'll see the table return and the vertical actuator lift back to the home position. All right. All right. So now we've got that in there, and we've got our samples run. So the next thing I can show is the software, and I can bring up some of the extrusion profiles that we just ran. But here is one of the baseline samples that we extruded. And if you notice on the edges, it doesn't have a smooth run. It kind of, the grease kind of opens and closes. And it's what we kind of call a shark toothing effect. And we just see that in new greases in varying degrees, depending on if they got different levels of tackifier, and then that can cause them to kind of hold differently. All right. So just take this. I'll be able to use this. So we've got our software on the computer. We're able to use this to look at our samples. So we highlight that one. We'll import, connect, and then we'll bring in one of the samples that we just ran. And then give it an ID. So we'll just call it GT for our boot camp with today's date. And then we have different areas in the software that can be filled in. So I put myself as the operator. There's a spot for customers, the sample location, information about the equipment or type, OEM, application, and the baseline. And there's where you're able to assign a baseline to the sample. So you're able to add as much as you can get from your customer. And then when I pull that up, so here we see that 3 different profiles. So we've got the first profile we see the increase in force when the speed changed and increased. And then the third profile, we see it decrease. And that is a pretty much perfect looking grease thief graph. So then I can go on here and see if I can find some different ones just to share. So here you'll see in the third section, this one has a small little peak, and that would be from a buildup of particles in this sample, and then those would have been the increase in pressure when those particles would have come out. So this is where we're able to go in, and then in the software we've got the data points. We're able to go in, and we would be able to disable those points so it wouldn't count that increase, and it wouldn't influence the true reading of the grease consistency. So this is kind of how we're able to use the software and able to provide that that feedback for our customers. So just to show you what it looks like too, I'm going to add a baseline. So I'm just going to pick a random baseline and add it on there. And we're going to look at that. Wow. I don't know if I could get that lucky ever again, Rich.
Good selection there, Richard.
So here we see this sample and baseline, and it might be hard to see, but that's because they're almost overlapping each other. So
yeah, you have a kind of a red line and a blue line there, don't you?
Yep. And we can see at the beginning that the baseline's the red line. It took a little less force to extrude. The sample took a little bit more. But then once it got into the higher speed and the medium speed, they're just about a perfect match to each other. So yeah, this GTI would be very, very close to 100. And 100 is kind of our goal. Obviously, we're not going to always be perfect as the reference lube is. But the closer you are to 100, the closer your grease is going to be performing as it's intended and as you want your equipment to be running. And as our GTI or the grease thief index gets lower, then our grease is going to become softer. Some applications, this is normal and expected. So for example, in a wind turbine, we might be expecting the grease to drop quickly, and you might see a drop somewhere, a GTI of 60 to 70 right away because the grease is getting beat up, but then it will hold that level, and that's kind of normal. So that's also the important thing, like oil analysis, is establishing a trend to understand what is normal for that application, because not every application is the same.
Up with something as just as a general guidance, and we kind of chose plus or minus 20% of that GTI, so that so basically the index, like you say, 100 is near identical. So we'd say greater than 120 or less than 80 would be flagged as being significantly enough different than that grease. But in some applications, for example, in wind turbine main bearings using certain types of greases, we saw this natural tendency of the grease to soften without a real corresponding performance impact. And so there we adjusted it to plus 120. I think it was like minus 70 or, less than 70 or less than 65 or something like that. And it was just, had to be developed over time. So there's no real absolutes when you look at this, because greases behave differently. But the nice thing about this particular technique is you're always referencing back to the new grease, the grease that's in that condition when you first put it into the machine, and you're looking for changes over time. And not only just this general kind of softening and hardening, but also what about the tendency of that grease to separate, which initially it could be softening, but then later becomes hardening because you lose a lot of that base oil. And I've seen other laboratories look at things like determining a ratio of oil to thickener and saying, oh, this is the oil to thickener ratio. And then in a used sample saying, well, that has changed to a certain degree. But what I struggle with in that approach is that Well, what is that criteria? How much of a change in the ratio between thickener and oil is going to cause a problem? And that becomes the challenge, because most grease formulations are mostly oil. Could be 70, 80, even 90% oil with just some thickener to keep it in place. So you could have quite a bit of variation there. But what we're looking at is the dynamic flow behavior. And you just showed us right there a real good demonstration of 3 different greases and being able to compare them to how that new grease performs, and how a sample that's been in a machine for some period of time, does it continue to perform in that way? Has it degraded? Has it changed in either of these directions, which both can cause problems? Hardened greases, stiffer greases that don't flow like they should, don't necessarily kind of slump into the bearings or the gears to continue to provide that oil and additives that it needs to lubricate, or in the opposite side where it gets so soft that it really isn't performing that grease function anymore of staying in place. And that's why we use greases, right? Because we want to pack them in. We want to put them in place. We want them to stay in place. And this is really a great test that helps us say, is this grease still doing that? Is it still performing as it is intended, as it is formulated, as it needs to be for this application? Or has it changed? Do we need to look a lot closer at it? So that was real helpful, Richard. You showed us the way to use the analyzer. You shared some data with us on how that data then gets compared to the baseline. And we've talked a little bit about developing criteria, having maybe a default criteria plus or minus 20% of that 100 index value, which would be our target, but also about changing that when it needs to be somewhat different depending on the specific application. So now you're pivoting. You've moved. We're leaving a grease thief analyzer behind here, aren't we? You've pivoted to a new machine. What's the difference here? So you got to put you're muted again. So you got to get that back on.
I did pivot. The analyzer that's next to us here has the newest camera. This is the newest generation unit. So you notice that this camera is just a little bit bigger than the one that was in the other unit. And I just wanted to show off both units so that way everybody got to see them both. And there we've got the LED controller there next to it. So if you see here, there is the cutout in the table that I was mentioning earlier where the substrate sits. And this hole is completely through. And underneath here is an LED light. So that little white panel in the middle there is an LED light. And in a minute, I will turn it on and we'll kind of show that flashing. So that's going to illuminate from the bottom. And then on the top, you have this camera. It's going to be taking a video, and the light will automatically adjust its pulse width and intensity. And we'll review this again later when we're running samples. But that's going to allow us to increase the light to an appropriate point for each sample uniquely, because every sample is not the same color. And that's going to allow us to, I guess I can leave that open for now while I show you guys this. But it'll allow it to adjust for each sample uniquely so that you don't have to have a set standard level and then each sample is different and you might have a problem. This allows it to automatically adjust itself to a sample, and then you're going to be able to perform a really nice particle count on the sample. So I'm going to load our sample up on the tray here to particle count.
Now, Richard, there's obvious differences here. Can you talk about? We're actually in construction on this unit, right? We're partially assembled, and you're focusing. It's missing a few parts, isn't it?
Yes, there's currently the vertical actuator that you saw in the other video that was applying the force. Is currently on its way back from the manufacturer after getting a little bit of TLC.
Okay.
And we will then have it back in, and then this won't be able to extrude as well. So that's
a key difference Yeah, but a key difference I saw here was that you said this is the latest iteration of this,
Oh,
and yeah, and it has that offset of the actuator that moves that table back and forth, right?
yes. Thank you very much. That is correct. So previously, the generation that we were using before, and I can kind of just sneak the camera back over there and show you guys, the table is sitting right on top of that actuator. And before, that caused us to have an extra step where we would have to, at the end, then push the sample out further to be able to run it over the old camera and LED controller. And then in the new unit, the new and improved, we're able to, I'm sorry, I got my door stuck on the top. We're able to have the sample offset. So it's not sitting over top of the actuator's out front, the sample's behind it. And this allows the camera to be closer to the die extrusion. And then once the sample is run the whole way across, we're able to perform that die extrusion instead of having to then get it further out there. So it just is a little bit more helpful, and it saves time and steps in the new generation of the unit.
Yeah, it's great.
Okay.
An improvement here, and really streamlines that analysis process. Makes it quite easier to do to really do both aspects of what the grease thief analyzer does for us, right? And I could even say it's three things. One is the die extrusion that you just showed us at the other machine. Second is the particle counting that you're going to share with us now, and then third is this whole preparation process, right? It's taking the grease from the sampling device and creating this thin film. And you're going to pivot next to show us how you use some of those substrates to do the other tests around the lab. But for now, walk us through this particle counting process, if you would.
Yes. So the first thing that we need to do is turn on the LED. So in the software, I will just go to the LED controller, and then I will enable the LED and send that over, and then we will now see that start to strobe. You guys see that strobing?
It's not obvious from that angle.
The camera might not want to pick up the strobing light.
Yeah, it might be the framing rate of the camera. It doesn't quite see that, but I can confirm I've seen it, and it does have that kind of effect to optimize the illumination of the particles, right?
Yep. And I can also share the software screen, and that might show the particles a little better versus this camera for this situation. If you want, Rich.
Oh, there we're actually seeing a little bit of the strobing or the illumination now. Mm-hmm.
Okay. If you'd like, I can share the software screen, and then you would be able to, I can share the software kind of adjusting and then running the samples, and they'd see the kind of the boxes on the particles. Should I show that?
Yeah, let's do that. Let's show that. I think that really helps us understand what's going on here.
Yes. So, all right. So I'm going to share my screen. So we're going to be able to see the software. So to turn on the LED, I just simply went to my tools and the LED controller. And then here I enabled it, and then I hit send, and that turned on the LED. So it's nice and simple. And then the next thing I'm going to do, my sample's in place, is I'm going to click on the live analysis.
Hey, Richard, can you turn the other camera off temporarily? Oh, actually, that's from the, I don't know if you can or not easily, because now there's a few different screens sharing the width. If it's not easy to do, let's not be too disruptive. But I'm just trying to give maximum view of the screen that you're sharing here.
I think I did it. Okay. So we can see that it's adjusting on this baseline and kind of everything's disappearing. And that's a good thing because that means there's nothing in this baseline. So if you don't have any particles, it'll look completely, the screen will look completely white. So that's why I wanted to start with this one to kind of show a baseline sample, and then we'll work our way, and I will have some other strips that have some more stuff in it. So here, we're ready then to start. So we would return, and then we can see slowly moving. You can kind of, every once in a while, you'll see a vertical line, and then there was a fiber I saw kind of moving by, but that's a good thing. And then there we see the end of the thing. So we're going to hit stop, and that stops the live analysis. And then that automatically, that file gets saved. And then after we run a couple samples, I will pull up the files, and I can kind of also share that, what that looks like. All right, so I'm going to go ahead and I'm going to pull that sample out, and then I'm going to start, and I'll get the next sample loaded. But the nice thing about the particle counting is, and we'll show this in the report, but the software is an intelligent software. You can kind of see that at the top. It's called CantiVision Intelligent Analysis, but it's able to classify the particles. So it's looking at different characteristics of the particles. So different things like the aspect ratio, or it's different dimensions. So it's major dimension or it's minor dimension. And it's kind of just taking a lot of these different particle characteristics, and it's looking at those, and then based off of what the software knows certain particles look like, it's able to classify those particles when we do our analysis with the software. And I'll show that in the report at the end, but you'll kind of see a classification of normal particles. So these are particles that are not going to be severe wear particles, or cutting or sliding wear particles. They can classify and pick out fibers. And then it is also able to pick out air bubbles in the sample. So if there's an air bubble, it'll know the difference between an air bubble and what that looks like versus an actual solid particle. And so that's really helpful in making sure that you're getting everything counted. But then when you're doing it, it's where kind of the intelligent or the smart particle counting comes in, is that you're not getting a really high particle count because there was a lot of air bubbles in your sample. You're getting a particle count that's reflective of the actual particles in your sample. All right, so I've got the next sample loaded up. So on here, again, all I'll need to do is click on my live analysis button. And then again, this is going to pop up the automated background adjustment. So here at the bottom, you see it's adjusting the pulse amps and the gain. And then here you're seeing the adjustments to that background measurement and the standard deviation. And it's kind of got a goal number that it's working towards. That way, samples are being run and analyzed in a very similar fashion. So it's green, ready to go. So here we see particles. And as I return the tray, you're going to see the screen light up green around the particles that the software is counting. So this is how we know that it's working, that we only have green circles around particles that we're seeing. We're not having green circles around nothing. So I get to the end, I hit stop. I stop the capture, and that video is automatically saved to our server or computer location of your choice.
Quite a different scene on that video, Richard, than the first one you showed us.
Yes, and I know that that one was a little bit of a controlled one, but that one was approximately 1,000 parts per million of iron content.
Oh, as a reference point. And of course, particulate doesn't necessarily correlate directly to the iron parts per million, but in this case, it just gives you a sense of what's going on there, right?
Correct.
Yeah, because you're seeing all sorts of different things. On the first one, you picked out a fiber, a big fiber, which in retrospect may have just been an errant fiber that got stuck on that grease at some point. Probably didn't have a lot to do with that grease in general, which was otherwise real clean. But here you've got a pretty significant particle population. It could be wear particles, could be rust. It could even be non-wear. It could be just dirt particles or sand or something like that. But in this case, we kind of knew what we had here, right? We had some iron-containing particles that made up the majority of that particle population, right?
Yep, that's correct. And then I got a third one to run, and this one will have even more interesting things to look at. So just getting the tray prepared for that.
For me, the really fascinating part about this capability goes to, what this can tell us about new greases. And when I say new greases, yes, I am talking about new in the package, but I could also be talking about greases in a grease gun. Could be talking about greases that are in an auto luber system, greases that are in a single point lubricator, these gas powered units. And so, in other words, anywhere the grease resides before it gets into the machine, if we can get some insight into particle levels, it really gives us a chance to treat greases much like we're treating oils on a regular basis in advanced programs. But I'll let you talk about this one, Richard. It's pretty wild.
Yeah, this has got some big stuff here. I'm actually just pulling this by hand because I know there's some air bubbles in here, and I wanted to kind of show. So I'll try and get it back to a point where I'm seeing an air bubble on the screen. So, oh, camera's delayed. I almost had it perfect. So there on the right side of the screen, we can see the air bubble that's stuck in this sample. And we know it's an air bubble due to that ring on the outside, but the light is coming through the middle. And this is just known, the Canty, who is purveyor of the camera, has a lot of history with oil analysis. And then we're able to establish that. And the software, like I mentioned, would be able to discount that particle. And it's not going to count it to your overall particle count and make it seem like you've got this very, very large round particle. It's going to understand that perfectly round particle is an air bubble stuck in your sample. So that's kind of where we get the idea of the smart particle counting from. So I just wanted to kind of point that out before we ran the sample. So
the question about, what gets counted as a particle. And, in some respects, when you think about what grease is, grease can be a distribution of what could be thought of as particles that are thickener particles. And even just these soaps, can be thought of because we mill them down, when we're making greases. But here, what we're talking about is assigning kind of the translucent behavior of that medium, of that background, of that material, which is the oil and the thickener and so forth, kind of sending that into the background and then picking out the discrete particles that are separate from that are different material, that are metals, that are contaminant particles, that are dirt, that are fibers, and all these different things. And using this smart intelligent vision analysis to differentiate, including the air bubbles that you talked about there.
Yes, it's very helpful to be able to identify, and then it's also nice to kind of like what we, going back to our analysis, you want it to be that trending analysis. So it's nice to be able to, over time, also being able to compare and understand, is there a change in our particle count? So similar kind of in oil, where you've got a DR count where you're trending that wear. Specifically, as you mentioned, we're picking up anything that is a solid particulate. So if it is a solid piece of material and it's blocking the light, it's going to be counted as a particle. Whereas if it's a very translucent piece of material or something like that, where it's not an actual solid material and it's not blocking the light, it will not be counted as a particle. So it's not, as you mentioned earlier before, Rich, when I mentioned the iron dust, it's not saying that there's, it's not saying what the particles are specifically as far as the metallurgy, but just that it's classifying that you do have this many particles, and it's able to classify what they look like based on its knowledge about history of particles.
Yeah, and also too that we don't want to overlook the fact that you're when you're performing this analysis, you often have other test results at the same time, such as the ferrous content. And maybe we'll get a little time today, even just to briefly introduce what the FerroQ device and how that gives us a parts per million of ferrous debris. So you could imagine where you have an environment where you've measured ferrous content, it's very, very low, and yet you have a particle response like you do here. You start to think about, well, they're not wear particles, then they got to be contaminant particles, and where could they be from? So you can infer a lot about the conditions that you see here, and it might be enough to create some kind of conclusion about what you're finding there, or it might be enough to say we want to do some additional analysis, right? We may want to separate the particles from the grease. Now that takes time. It takes chemicals and some expertise in looking at these individual particles under the microscope. But it may be warranted by what you could see in this kind of scanning and intelligent particle identification that we get from using the software and using this capability as part of the Grease Thief Analyzer. So for me, that's really exciting, where we learn to put these different measurements together and what they mean, in addition to this categorization that you're going to show us now that happens within this particular analysis of the Grease Thief particle counter.
Yes. So here we've got the report. So this is simply, as I mentioned, taking the raw data that the software outputs, and you've got all the things at the top that I talked about. So there's a lot of different things in here that would be boring to talk about everything right there, but this is the convenient where we boil it down. We take all that raw data about the particle, and we're able to extract out the values of what we need to get to our customers. So the squares you see highlighted in blue are what would be reported out to the customer. And so starting on the left side here, we're seeing the concentration of particles. So we have the particles that are greater than 10. This is somebody has a typo in here. So particles greater than 10 microns, the particles that are greater to 25 microns, and then the particles that are greater than 80 microns. And so it's not the same thing. Some of our customers in the past have said, oh, this is ISO 4406. This is not the same thing as ISO 4406. It's similar, where there are 3 different and distinct particle ranges that are important for grease lubrication to monitor. And depending on the application, it's going to be important to find your levels.
Well, there we go. We worked through that just about 1 hour video presentation that we had done from a previous Grease Thief boot camp, and we did want to share that with folks today. I'm looking for any questions that have come through. I'm not seeing any at this point, but I would just like to take this time to kind of, reiterate that this is a technology, this is an analysis that really is targeted at greases, and greases are different than oils. And so we've got a number of laboratories around the world that have incorporated this into their testing offering. And we've seen this applied effectively in applications including wind turbines, locomotive wheel bearings, pharmaceutical manufacturing facilities, robots, and all sorts of other production and manufacturing applications where we have critical components that are grease lubricated. The Grease Thief Analyzer that you saw demonstrated here today is around the world. The laboratories that have this and offer this include SGS in Vallejo, California. It's Polaris Labs in Indianapolis. ExxonMobil is performing this analysis at their laboratories in Sarnia, in Canada. Of course, our laboratory here in Pennsylvania, MRG Labs. And then overseas, you got a number of folks that are using this technology as well, and that includes Bureau Veritas at their facility in Spain. We've got the folks from Ecol that are testing in Poland and serving Europe as well. And then we have Running Land Labs in Shanghai, in China. And, and there's more interest, growing as time goes on, and as more end users are looking for solutions to monitor their components. So again, thanks for joining us here today, whether you watched us live or you were, picking this up as a later recording. Feel free to reach out to find out more and learn more from us. Call us at MRG Labs. It's area code 717-843-8884. Or you can check things out on our websites, greasethief.com and MRG Labs, MRG Corp, MRGCorp.com. Have a good day, and we'll see you a month from now at our next Grease Thief Thursday.